Okay, now continuing this story, here we go. We have a line, something must be else. This is a new story. When we know K1 and K2, now we've just computed them. We don't know if they're the truth, but we're going to assume they are for the moment, that they are the truth. Then we can actually use curve fitting to do an assay, to measure the amount of F present in some reaction. So if you know K1 and K2, and somebody tells you some amount of B data, the bound data, we can use that information to measure how much F was given to us, which is not 20% of the B data, B amount. It's whatever this curve that we're going to see predicts. So, for example, suppose we have the data given above that we had, the actual data, and that we know K1 and K2 as we determined, but imagine we don't know the value F0. Now remember, F0 was actually 1 when we did our curve fit. So let's suppose erroneously that F0 is 0.5, and let's see what curve fitting tells us F0 should be. So here we go. F0 is set to 0.5. That's our guess. Throw away our prior graph. Now, all graphs in MLAB, if you don't say otherwise, are called W for window, as you can imagine. So this says throw away the MLAB graphics window, W. Oops. And here, again, we jump to the view quickly. Here is the command that draws our data again and the guessed model when we have F0 equal to 0.5. So here is the data drawn again the same way we drew it before. Here is the graph of our guess when we have F0 equal to 0.5 with K1 and K2 defined as computed above. Here's a title that tells us about that we put in the program. And here's what we see. So given this exact data we had before, but assuming, erroneously in fact, that F0 is 0.5, this is what the model predicts. And it isn't the truth, as you can see.
No, there's a clear disconnect, right?
Right, exactly. So now continuing, we're going to do fitting to find out this time what is F0, not what is K1 and K2, but what is the correct F0. So we fit F0. Notice this is fitting an initial condition. This is, well, no, this is fitting a parameter. We could fit initial conditions, I guess, is the point I was going to make, but this is not an initial condition. This is just a parameter. But we fit to find F0 by fitting B to the data D with the same weights and honoring the constraints. And guess what? We get back to almost exactly what we started with, which is nothing but essentially a partial confirmation of the fact that this is a it's a unique model. This point, K1, K2, F0, G0 in four-dimensional space is essentially unique. You can't go far away from it and maintain a minimum sum of squares. So this comes back as it should in a good, well-defined model back to the original F0.
So we move forward and we move backwards. We proved it in one direction?
We proved it in one direction, and we proved that it was a semi-unique answer in the other direction by being able to get right back to where we started from.
Very good.
Now, but this, if we didn't know F0, and we did have this data, this would have been the assay that says you have 1 molar unit of F0, or of F, rather. Okay, so now continuing, now we will graph the best fit model again, and guess what? We get right back to the same one we had before. So there we are, but continuing, and here's a remark, a comment that says what we just said verbally. The above computation just verifies that the solution is a nice local minimum or sum of squares, and you can't change these things very much and stay minimum. A more practical assay is what we're going to look at now. Suppose we just have one value of B, which is 0.112, taken at 4 minutes, which we know from our picture is out near the equilibrium. It's out where this is pretty flat. So at equilibrium or near equilibrium, we have measured an amount of B, 0.112, and we want to know how much F was provided when we know that there was 1 molar of G provided in the reaction. This could be a lab test where this is a reagent used in the test and there's 1 molar used, and this is the unknown amount in our sample that we're trying to assay. So we continue. We throw away our picture again because we don't want to see it. And we look at this single data point. So now we make a matrix D1. The first row and the first column is 4 times 4. Remember, we said 4 minutes. And the first row and the second column, that makes 1 row vector of 2 elements of D1, is 0.112. This is the single row data matrix, single point. We guess F0 equal to 1. Now, for this case, this turns out to be not what it is at all. We take a time vector now. We want it a little bigger so we can see the picture a little further. So we go 0 to 5 in 200 steps. And now we draw the data. There it is. D1 is the 1-point data matrix. It's a circle. Has a point size and a line type of none. Draw, again, the actual curve that we predict, given the parameters we have at the moment, with the vector of times TV1. Remember, that's 0 to 5 now. And put a title on the graph. And here is the picture. There's our single data point. And this is our curve that we think we have if we have these values for all the parameters. Certainly not the truth at all. And we're going to try to find out how much F0 we really did have. So we come over here and we fit the model. Again, same idea. This fit F0 again. But this time we compute the true unknown amount we started with, which is 0.48 something. And we have a very nice error in this particular case, and this is because we can fit perfectly.
That
with
is
one
virtually
point,
perfect, yeah.
with 1 point, you can fit perfectly. You never have to have any deviation. So of course, this error estimate probably is meaningless, and this best weighted sum of squares is meaningful. It is very small. Okay, so continuing here, our assay. So here's the F0 we computed by the curve fit. This fit changed it, and there it is, 0.48 molar units of F in the sample. And now we're going to graph our best fit model, and of course it fits perfectly, and there it is.
Absolute perfect fit, right?
Yeah, as it should be. And so this is one of the things you can do with modeling, is to use the results of your modeling to build an assay for later use.